Hello, everybody. Good afternoon. And this is our office hours time. And I thought that we could go over multiple choice questions. If you are joining in late, please watch quietly and you can reserve your questions towards the end, not interrupt in between. You can mark down the question numbers that you want from these multiple choice questions to be answered. Or else, if you want to ask a question, raise your hand with the little guy in the corner. All right, so I'll go ahead and explain the multiple choice questions for chapter number 6. So chapter number 6, as you all know, is a work, energy, and power chapter. So you should expect multiple choice questions pertaining to these concepts. So our first multiple choice question is it possible to do work on an object that remains at rest? If an object is at rest, does it do any work? So basically you all know that, yeah, if it's not, there is no motion, there is no work done. Force times distance, no work done. So you know which one to click. The next slide will show you the answer with the explanation. That's how we do it. Work requires that a force acts over a distance, and if an object does not move at all, there is no displacement and hence no work done. This was simple. Then we move ahead with the next one. A box is being pulled across the rough floor. So at a constant speed, now remember this is constant speed, what can you say about the work done by friction? So take a little while. Does friction do any work? So a box is being pulled across a rough floor. So rough floor means there is friction, and work done is equal to force times distance into cosine of theta. Now you know that friction is in a direction opposite to that of the applied force. So force of friction this way. The angle between the two is actually 180 degrees. So theta is 180 degrees. And if you put 180 degrees over here, you will get minus. So the work done is negative, that is less than 0. But yes, the work is done. So friction does negative work. So the next slide will show you the answer and the explanation. Go ahead and read this part. So next, a baseball game. The catcher stops a 90-mile-per-hour pitch. What can you say about the work done by the catcher on the ball? So there's a catcher and there is a pitch. So what is the work done by the catcher on the ball? So the ball is striking the catcher, and what will happen to the displacement part of this? We did a problem in the problem section. When the ball strikes the glove, what happens? So what kind of work is done by the catcher? Again, the catcher is going to push the hand backwards, and the work done will be therefore negative because the angle between the force and the displacement will be 180 degree, and hence your answer should be negative work. The catcher does negative work. The force exerted by the catcher is in a direction opposite to that of the displacement of the ball, hence the work done is negative, but work is definitely done. So next multiple choice question is, a ball is tied to a string. So there's a ball which is tied to a string, and it's being whirled around in a circle. So it traces a circle. It's at different points and different times, and it has tension at different points with the motion. So it's displacing this way, but the force is this way. So you can understand displacement is this way, force is in this direction. What is the angle between the two? We know that work done is force times distance into cosine of theta, and theta is the angle between the force and the displacement. If this angle is 90 degree, you have done no work. Work done is equivalent to 0. So a ball tied to a string is being whirled around in a circle. What can you say about the work done by the tension? So that's it. The tension does no work at all. So you can look at the explanation here and the same stuff that I was explaining, and it's a better diagram than what I was drawing. So then let's go ahead with the next multiple choice. You lift a book with your hand in such a way that it moves up at constant speed. So at a constant speed means you're raising it in such a way that you're not accelerating. So that means acceleration is 0. While it is moving, what is the total work done on the book? So how much amount of work is being done? You can take a minute to think about the scenario. Is there any work being done? The total work done is 0, since the net force, which is mass times acceleration, is 0, and the work is done by the hand, which is positive, while the work done by gravity is negative. The sum of the two comes out to be 0, and there is no kinetic energy basically. So the entire energy is in the form of change in potential energy, and it comes out to be 0 because there's no net force acting. Hence, work done is 0. Go ahead and check the explanation in the next slide. So then we move on to next one. By what factor does the kinetic energy of a car change when its speed is tripled? So if kinetic energy was 1/2 mv squared, and initially if your speed changes to 3 times v, if it's tripled, what will happen to kinetic energy? So the old kinetic energy and the new kinetic energy will be 1/2 m times, but instead of v, we'll write 3v whole square. That is 1/2 mv squared, but there's a 9. So this represents that it is 9 times the old kinetic energy. So the kinetic energy increases by 9 times. Think about it and go ahead with the solution. It shows you the answer as well. Okay. And then let's move on to another problem. So we have car 1 has twice the mass of car 2, but they both have the same kinetic energy. So it's possible that if a car 1 and car 2 are moving in such a way that both have the same kinetic energies, but their masses can be different. That's possible. So how will we solve this to find out how speeds compare? What should be the relationship for the speeds of the two of them if their kinetic energy is same? So if this is car 1 and this is car 2, both the kinetic energy of this one, car 1 is equivalent to kinetic energy of car 2. But the situation with car 1 is if the mass is m, the mass over here is 2m. So the kinetic energy is given by what? 1/2 mv squared, right? And this one is equivalent to, we will write down 1/2 mv1 squared because we know the speeds are different for car 1. And for car 2, the speed will be 1/2 m. But we know that the car 2 has double the mass. So I'll write 2m for this one. And v2 squared. So 1/2 and 1/2 will cancel. M and m will cancel. So v1 square will equivalent to 2 times v2 square. So how do their speeds compare? So if you look at that, if I have to rewrite this whole thing, how will you write this one as? Or is it saying car 1 has twice the mass? Oh, I did the other way around. So it is car 1 and this is car 2 and this is car 1. So v1 and v2. Therefore, v2 must be square root of 2 times v1 squared, which means v2 is equivalent to root 2 v1. That is option B. So you can see the detail here. Just read this carefully. Car 1 has twice the mass of car 2. Car 1 over here it's 2m. Okay, so check the solution, and it's explaining this here as well. Then let's go ahead with the next slide. Anthony is on a skateboard, and he's moving at a speed of 2 meters per second. After a force acts on him, his speed is 3 meters per second. What can you say about the work done by the external force on Anthony? Does he do positive work? Does he do zero work? Or does he do negative work? So we see that Anthony is on a skateboard here, and his initial speed is given. So his speed changed from, so his initial speed was 2 meters per second. And then once he must have gone up the ramp or down the ramp or what, his speed changed. The new speed was 3 meters per second. And if we have to find out the work done, we use the work energy theorem that we have used in many scenarios. 1 times change in kinetic energy is final kinetic energy minus initial kinetic energy, and you can find out the work done. So it's basically positive work because V is greater. So this is 3 squared and this is 2 squared. So the overall answer will be positive because speed is increasing. If the speed was decreasing, then the work done would be negative because the work done would come out minus. But since the speed is increasing, work done is positive. So your option A should be the answer. Okay, so you can find the explanation in a detail here. Let's go to next slide then. And those of you who are joining late, I just want to let you know that we are working on multiple choice for chapter 6. And the last presentation or the last video for this is already uploaded in the online folder. So this recording will also be uploaded along with the PowerPoint for this one. Okay, so the work, this is another one. The work accelerates a car from 0 to 50 kilometers per hour. How much work is needed to accelerate the car from 50 to 150 kilometers per hour? So if my initial work done, which is actually, if I look at this, these are two speeds given, which is change in kinetic energy, that is to mv square minus 1 by 2 mv naught square. You don't have to solve this, but you know that it's changing in a positive way. Then final work, like when he's increasing, he's accelerating the car from the change in kinetic energy is basically 1 by 2 again, mv squared minus 1 by 2 mv naught square. Here mv naught, v naught is 50 and final is 150. Here v is 50. Sorry, v naught is 0 starting from rest, and this is 50. If you look at this, the change between 50 to 150 is 3 times because 3 times 50 is 150. So he's asking how much work is needed to accelerate the car from 50 kilometers per hour to 150 kilometers per hour. So I guess it should be 3 times the initial work because this one is 50 joules. If I consider this as 50 joules, and then this is 150 joules, assuming mass is equal to 1. So assuming I have mass equivalent to 1 kgs, so we'll see that the ratio, the proportion is about 3 times that of the initial work. So go ahead and check the conceptual understanding. It's actually 8 times, sorry. Let's call the two speeds V and 3V. So because the speed is increasing 3 times. So let me go back to this part. The work W naught accelerates the car from 0 to 50 kilometers. How much work is needed to accelerate the car from 50 to 150 kilometers? Sorry, basically the speed is changing to 3 times V. All right, so that means the energy will change 9 times. So if initial work was 1 by 2 mv square, then when the speed changes, this becomes 9v square minus v square. So it changes 8 times. Yeah, I was looking at the velocity, but it's the work is changing 8 times. So be careful and disregard the explanation in the previous slide. This is the correct version. Then we again go to the next one. There are two blocks, mass M1 and M2. Mass M1 is bigger and it covers a more surface area on the floor and have the same kinetic energy. So it's saying mass 1 and mass 2 has the same kinetic energy. When they hit a long stretch of a rough surface whose coefficient of kinetic friction is 0, which slows them down to stop. Which one goes farther? So which one of the two do you think will go farther? So with same kinetic energy, so mass 1 has Ke as 1 by 2 mv1 square, and mass 2 has the same energy mv2 square. So which one will go farther? The force of friction by the first one is experienced more because it has more area to cover, while as the second one has a lesser force of friction to overcome. Hence, that one will go farther. So that's why we'll say that the friction force is less for M2, and hence, so stopping distance must be greater. It will go faster compared to the first one. So that's your answer for that one. And then let's go to the other one. Is it possible for kinetic energy of an object to be negative? Can kinetic energy be negative? So to answer this, we just look at the formula for kinetic energy. It's 1 by 2 mass times velocity squared. So velocity is squared here. If I say I was going in the west direction and my friend was going in east direction, so this was 2 meters per second. For example, I was going in east direction and I had a speed of 2 meters per second. And my friend was going in west direction, had a speed of minus 2 meters per second. And both of us had mass of, say, m. So what will be the kinetic energy? 1 by 2 m. Although our kinetic energy will be same, but will my friend have a negative kinetic energy? Let's see why. Minus 2 whole square is also positive, while as my kinetic energy 1 by 2 mv squared is also positive. So kinetic energy, just because v is squared, will always be positive. All right. So the answer is no. It can never be negative. It has to be positive always because of the square in the velocity. So is it possible for gravitational potential energy of an object to be negative? So think about this for a little while. Gravitational potential energy, as you know, is given by formula mass times acceleration due to gravity in h. So you can measure gravitational potential energy either from top to bottom or from bottom to up. If you're raising a certain object from ground all the way up, then still it has its potential energy is increasing. And when an object is falling from a certain height, its potential energy is decreasing. So you get minus mgh while you get plus mgh. So think about the two scenarios and answer this one. So by now you must have guessed that gravitational potential energy, where height h is measured relative to some arbitrary reference, where potential energy is 0. For example, a book on a table has positive potential energy if the 0 reference level is chosen to be floor. However, if the ceiling is the 0 level, then the book has negative potential energy. Remember, I used to do projectile motion problems, and I would always choose this as my 0 point, and I would choose the height downwards as negative and any height upwards as positive. So we choose a reference. It's up to you. If you choose this as positive and downwards as negative, obviously your potential energy will be negative. If you choose upwards as positive and downwards as negative, then going up will be positive and coming down will be negative. Hence, is it possible for gravitational potential energy of an object to be negative? Yes, it is possible. Two paths lead to the top of a big hill. One is steep and direct, while the other is twice as long but less steep. How much more potential energy would you gain if you take a longer path? This is a conceptual question. So I have there are ways to reach the mountain, and there's a shortcut path which is steep, but the height is still same. And the height staying same, but there are other trails which are like less steep and longer. So there were other trails, and I just wanted to reach quickly, so I took the steepest path. Does it mean my potential energy over when I reached was higher, while as my other friends took a little more scenic path, which where there were ups and downs, it was not that treacherous of a height. So they reached the top too. So the height is h. It's the same. So it was 200 feet, and this was also 200 feet. So potential energy is m, g, and h. Do you think the potential energy in scene 1 and potential energy in scene 2 is different? It really doesn't matter, because the height is the determining criteria. Height for both of them is same. So your potential energy wasn't different. Your potential energy, whether you take the steepest path or a more easier path, doesn't matter. It's going to be the same. Okay, so then we go ahead and see the answer. You already know the answer for this one. And then we go to the next one. How does the work required to stretch a spring 2 centimeters compare with the work required to stretch it 1 centimeter? Is it going to be same work to stretch a spring by 2 centimeters, or is it going to be different? Think about it. Let's have a spring. So if this was the initial position of the spring when it was not stretched, then I stretched the spring, say, by 1 centimeter. And then next, I stretched the spring, if this was initial position, by 2 centimeters. What do you think is happening to the work done? Understand this is elastic potential energy, which is 1 by 2 k times x square. If you are increasing the distance, you're doubling the distance, what will happen to your work done? So will your potential energy increase twice or 4 times? So since one was 1 by 2k x squared, that was 1. The second one was 2. You must have guessed the answer. It increases 4 times because the 2 gets squared. Coming to the next one, a mass is attached to a vertical spring, causes the spring to stretch and the mass to move downwards. So this is a different scenario now. This is a vertical spring. So the spring is like this now, not horizontal. In the previous question, you stretched it horizontally. And how can I stretch it horizontally? I'm putting in more masses to it. So what can you say about the spring's potential energy and the gravitational potential energy of the mass? So is potential energy of the spring increasing, and is the gravitational potential energy also increasing? What is gravitational potential energy? You have to understand the formula first, mgh. And what is the elastic potential energy? 1 by 2k x squared, right? Oh, sorry. So the spring is stretched. When the spring is stretched, x is increasing, so it's getting squared. But when the spring is stretching, its height is falling, so the mass is moving down to a lower position. That means potential energy is decreasing due to the gravity is decreasing, while as stretched spring PE, or due to the spring, is increasing and gravitational potential energy is decreasing. So that is the explanation for this one. then you come to the next one. This is slightly tricky, but do pay attention to the formulas. There are 3 different balls that are falling from height A. You can see the height for all of them is same, but the slope is not the same. The 3 balls of equal mass start from rest and roll down different ramps. All ramps have the same height. Which ball has the greatest speed at the bottom of the ramp? So how will you work on this? If you have to find speed, we will go ahead and use the energy conservation principle. This is a gravitational potential energy and kinetic energy change problem. So at the top, the energy is entirely potential. At the bottom, when it's just about to reach bottom, energy is completely kinetic. So let us consider that the ramp does not have any friction. It's smooth surface. Initially, it was at rest, right? So we say the change in kinetic energy is initial kinetic energy 0, and initial height mgh naught is higher, and this is 1/2 mv naught square. Now that I'm writing the whole thing, so initial kinetic energy is 0, final height is 0. We have done problems like this in chapter 6. Minus mgh naught equivalent to 0. So if I have to find the speed, what do? I take this on the other side, 1 mv squared equivalent to mgh naught. So v in all cases will be equivalent to 2gh naught 0. See, it does not depend on, the speed does not depend on the path. It depends on height and acceleration due to gravity. So now that you know this explanation, which option will you choose? Is it A? Which ball has the greatest speed? Is it A? Is it B? Is it C? Or is it D? If you've understood the math, you will understand the speed will always be C. It's only dependent on H, which is same for all of them, and acceleration due to gravity is also same for them. The situation would have been different if there was friction also involved. Then the scenario would be different because this would be longer path. If I included friction, then you have to find out the work done by force of friction. But since in this chapter we are doing only conservative forces, we are not doing non-conservative forces, so you're not finding work done by the non-conservative forces. We are assuming that to be 0. Hence, the velocity at the end of the path will be same for all of them. And this is one of the explanations given, the same thing that I was explaining. And then there is something like, this is a common thing to see in water parks and all. Paul and Corinne start from rest at the same time on a frictionless water slide with different shapes. So Paul is on a higher region and Corinne is on a lower region. Who makes it to the bottom first? Paul, Corinne, or both at the same time? Although this is an easier one, so because Corinne has already covered half the distance, so it will reach faster. It will reach, not faster, it will reach the bottom first. So even though they both have the same final velocity, their velocity at the bottom will be same because they have the same height, and we assume this is a water slide and the force of friction is not there. So they will reach the bottom at the same speed, but they will not reach at the same time because their start point was different. Corinne is at the lower height than Paul for most of her ride, and hence even if she has larger velocity during her ride, and therefore arrives earlier. So you can, this is more of a conceptual problem. Next comes, you throw a ball straight up in the air. In addition to gravity, the ball feels a force due to air resistance. So you're throwing a ball up in the air. You applied some force. So, and there was some air resistance. But since you applied some force and threw it up, then once it is at the top part, compared to the time it takes the ball to go up, the time it takes to come down is Is it smaller? Is it same time, or is it greater? Now it's under free fall, and the air resistance is still there. Now there is nothing propelling it to come down. There's no more force, additional force apart from the gravity working on it. So your common sense tells you that when it comes down, it takes more time to come down. Due to air friction, the ball is continuously losing mechanical energy, therefore less Ke and lower speed, and hence delay in reaching down. So the next one is Mike applied a 10 Newton force over 3 meters in 10 seconds. Joe applied the same force over same distance in 1 minute. Who did more work? And this is Joe. Mike applied some force over 3 meters. So distance 3 meters for 10 seconds. Force applied by Mike. And Joe applied same force F over the same distance, 3 meters, right? For 1 minute. Use your common knowledge about what we have learned. What role has time played in finding work? If you're thinking, I'll pause here. So do you see any relationship between time and work? Work done is simply force multiplied by distance. There's no mention of time here. And of course, the cosine of angle. Therefore, whether you apply the force for 1 minute or 10 minutes, it's going to be the same work. So I can safely say both did the same work. It's the power that depends on time, which is towards the end of this chapter you learned in today's lecture, which is uploaded on the Blackboard. You will see that we are discussing power. So let's come to the next part, electrical bill. That's more something related to today's lecture. When you pay the electrical company by kilowatt hour, what are you actually paying for? If you have not gone through the chapter that I had uploaded today morning, you can go back and learn about electrical energy. Basically, power is work done upon time. And work done is basically done at the expense of energy. So work done means energy over time. If you are paying electrical bills, you are not paying for power, you're paying for energy bills. Because if power is energy over time, multiply both sides by time. So T over here and T over here, your energy is basically power multiplied by time. I explained in the video today in the lecture that power cannot be, watt is a very small unit of power. So you have kilowatts because you have so many appliances that you use in the house, and your bill cannot be given for a second. There are so many hours that you use the electrical appliances and electrical energy for your household. So normally the time is taken as hours. All right. So therefore, electrical energy, where you see kilowatt hour, is not the unit of power because there's a power multiplied by time. Kilowatt is the unit of power and hour is the unit of time. So you get kilowatt hour, which is the unit of energy. So you get, the answer is energy. Okay, so go ahead and read through or listen to the lectures and do the problems, and this will be much better. Which contributes more to the cost of your electrical bill each month, a 1500 watt hair dryer or a 600 watt microwave oven? So some of you might be tempted to say, oh, it is 1500 watt hair dryer because it is 1500 watts, it is taking more power. But we have to remember, although work does not involve time, but power is very much work done by time. If you are using your hair dryer only for 5 minutes every day, then the power consumed over the month is not a lot. But if you are using your microwave for 3 hours every day. So let's do a little bit of math. If you use the microwave, say for 2 hours every day, and you use the hair dryer for 15 minutes, so power consumed by work over time, power is work over time. So which contributes more to the cost of your electrical bill? Electrical bill is not given by power, it's given by the energy. So that means you will have to get the, let me use the other answer slide because I'm running out of space. So you are basically paying for P is energy over time. You're paying for energy is equal to power into time. So if the time increases, your energy bill will increase even if you may have low wattage. So using microwave for more number of hours and using hair dryer for less 5 minutes every day will be different electrical bill compared to the microwave. It basically depends on how long you are using it. So that's the multiple choice part, and that's what I was going to discuss today for the office hours and basically an online kind of class. You should inform your friends and everybody that not to miss these sessions, because we could also do some of the problems. If you could tell me you have problem on any other chapter related problems for which you have to do the homework. All right, I'm going to stop the recording here and take your questions now.